Okay, now I'm live. Okay. Okay, I should be live. All right, I think I'm live now. This thing is something else. I'm just, fortunate that I have some means to stream with you, but YouTube doesn't make this any simple, or simpler, I should say. All right, we have more viewers. So I'm not sure if any of you have ever streamed, but you would think that you could just broadcast directly from YouTube. So what I have to do is I have to download a third party. And if I already explained this, I'm so sorry. But it's just, I don't know. I feel like it's 2020. We should not have, or I shouldn't have to use a third party to access YouTube Live. Hi, Dahlia. Hi, Elizabeth. Great, we are live. I hope everyone had a great week. It's going quickly. We're, 2 weeks into remote learning. I hope your other classes are going well, but aside from your classes, I hope everyone is safe. I hope everyone's healthy. It's really a difficult time right now, and, I just hope everyone in your family is doing well, your friends are doing well, and that you're doing well. So I posted some pictures on the stream. I'm not sure if you saw it, because what's happening is I'm basically sitting down in my dining room and I'm looking outside and there's a lot of birds and animals and all this stuff. So if one comes close to where I am, I take a picture. So I shared a couple of those with you. I think there was a cardinal and a squirrel. I don't know if they're, taking advantage of nature or taking advantage of my laziness because I have a cover on my patio table and it just accumulated water. But anyway, all right, so there's only 8 of you here today. That's all I have. Only 8? 9 comments? Uh-oh. All right, 10 more of you are coming. Well, that's good. And there may be a delay on my end. So I'm going to be posting the solutions to Chapter 3 for all of the homeworks. I already went in and I started looking at some of the homeworks that you have submitted. So that information is going to be updated on Jupyter fairly soon. Hi, Liana. And yeah, no, we're functioning. We're moving full steam ahead. It's now 2 weeks into this whole thing, and so chapter 3, going back to that, there's another section that I did not include because I thought that was just something that's outside of what's required. And I gave you everything that you needed for chapter 3. I'm not sure if you saw it in the class materials. All of the solutions that we spoke about for every single type of question, it's now been uploaded. Good morning, Valentina. So everything has been uploaded now to the class material, so you have solutions to every single question that we've gone through within the class discussion. Alrighty, so moving along here. So we're going to look at chapter 4, and chapter 4 is going to deal with functions. Again, we're still working with functions, but now we're going to be looking at different types. Inverse functions, exponential functions, and logarithmic functions. Alright, so looking here, we're moving along. So we're going to first start with inverse functions, but before we get to that, we have to look at what a function is. And if we don't have a good understanding of that, then it's just going to be a little bit tough to move forward. But as always, I provide some, really bad memes that I've come across. Again, I don't make any of these, so the only thing that I'm doing bad is sharing. So if we look here, this is basically functions in a nutshell, this graphic, and I think it does a pretty good job at describing what functions are and what they aren't. So we have what's called here well-behaved functions, and if you look, although they look like they're kind of crossing over one another, this would be a well-represented function. And if you look down below, where it looks as if like these, like, it looks like dots right now, but they're going to represent other things shortly. They look like they're bullying that one dot on the other side of, or in this other circle. So that's called poorly behaved functions. So we're going to talk about that. And then the classic meme related to functions. You said this graph was a function. The vertical line test determined that that was a lie. So yeah, no, really bad. I didn't make this. It says they're meme generator, not Alarcon generator. All I did was search. So moving along. So we're going to look at one-to-one functions first. And that's basically what that graphic is describing. So if we look at what one-to-one functions are, first of all, we have to define. So you have all of this. So if you look, before I move forward, this should be in Chapter 4 Learning Materials. This PDF, it's there. So if you haven't accessed it yet, I'll give you about 10 to 15 seconds to go into that part of our classroom, our Google Classroom, and just have that loaded so that you can reference this as we do it. Alrighty, so we have a relation. So a relation in the way that we describe it. Relation is just a set of points. You can think of that for lack of better words. A set of points, and here we have a set of points, and we have this relation called f. And how do I define relation here? Diagram, equation, or list that defines a specific relationship between groups of elements. That's the real, mathematical definition. But for our discussion, just think of it as a set of something. And in this case, the set of something is a set of points. So here's the relation. We have 5 points: -2, 2, -1, 1, 0, 0, 1, 3, 2, 5. So notice the difference in colors here. Some are blue, some are red or burgundy. I'm bad with names of colors and stuff, but it's close to red. Or maroon, I think they call it. Anyway, so we can form another set of ordered pairs from F by interchanging the X and Y values of each pair in F. So we call this set G. So F, you have a set of points, and now G, the only thing that happened is that XY became YX. So that's the only thing that happened. And can you confirm that my whiteboard is working? I provided a link. I hope it still works. Let's see. I'm going to type in. And please comment if you see this. I just want to make sure that the board is working. I just need one person to write the word that appeared on the board. So again, I'm just trying to determine if the whiteboard, the link that I shared, if it's working. And I just need you to comment on here the word that I wrote on the board. Can you hear me out there? Is this still streaming? Is it still working? Oh boy. So let me see. Let's see. I don't see anything on the board. All right. I had that fear. So let me just do this quickly. Hold on. I'm going to send a new link. Hold on, it'll be done very, very soon. Just give me like 30 seconds. All right. Oh boy. All right, I just shared it. I hope this works. So I just shared the link on our stream, our main page on the Google Classroom. Let's see. So again, thank you for commenting. I just shared a new link on our Google Classroom main page. All I need for you now to do, yes, thank you, Parthana. I'm glad you feel that way. All right, so it's working now. Good. Let's give it up for Parthana for saying Friday, or for writing Friday. All right. Wow, everyone's in on Friday. All good. Happy Friday. So, let's see. One-to-one functions, we're going back. It's working. I'm happy. And let's keep going with this. All right, so all that happened in this slide. F, you have the set of points. We're calling that a relation. And now G is another relation. And the only thing that happened was that XY became YX. So, moving along. So, to show that these two sets are related, G is called the inverse of F. So that's all that really happened here. So there was a switching of X and Y. I'm writing on the board now, right underneath Friday. So I'm going to highlight Friday just so that we remember. And basically this is what happened. That's all that happened. So we're calling that an inverse. But then if we think about that, relating it to geometry, that's a particular transformation. And if you remember what that transformation is, please feel free to write it. You can definitely chime in, and if you get it correct, or if you comment, I will comment as well. So XY becoming YX, we talked about this already. That's basically what's happening here. So you see how math is just all coming back together, coming full circle. But remember, the circle is not a function. I think we spoke about that. Kind of funny. Anyway, so to show that these two sets are related, G is called the inverse of F. For a function f to have an inverse, f must be a one-to-one function. So what does that all mean? So in a one-to-one function, each x value corresponds to only one y value, and each y value corresponds to only one x value. So something like this. So I'm going to go back to the original slide. So the first slide. So I'm going to zoom in. We need to see this happening. So for every point, or for every value, it can only relate to a single unique value, if that makes sense. So it's almost like for every input, there's exactly one output. That's what we're looking for. It's okay that they crisscross here, but they can't start doing this. They can't start ganging up on one of these values. If you see bullying in this relation world, then we have a problem. So think of it that way. So if we look at this example, I'm going to zoom out. So this function, so as an example here, this function is not considered one-to-one. So just look at it here. So if you look at the domain and range, 1 goes with 6, that's fine. 4 goes with 8, that's okay. For every input, there's exactly one output. For every x, there's exactly one y. So if we look here, in the domain, 5 to 9, that works also, but here, 1-to-1. So when we're ganging up, although yes, for every unique x there is a value of y, but now there's two x's, two different x's, but they're relating to this one output. So this function is not one-to-one because the y value of 7 is corresponding to two x values, 2 and 3. So that is the ordered pair 2, 7 and 3, 7 both belong to the function. So that's what's considered not one-to-one. And this would be considered one-to-one, this next example. So for every x, there's exactly one y, and for every y, there's exactly one x. So if that's happening, we call the function one-to-one. And look here, it looks kind of neat. They're not crisscrossing per se, but you can clearly see that for one x, there's one y. For one y, there is one x. Let's see. All right, so no questions so far from what I see. And again, if you ever have a question as I'm going through this, just please chime in because I'm reading the comments. All right, let's see. Going back. Where are you? Okay. Here we go. So here we go. One-to-one function again. A function f is one-to-one. A function if for all elements a and b in the domain of f, a does not equal b implies that a function of a does not equal to a function of b, or f of a does not equal to f of b. So we're going to look at that in more detail and what that means. So let me just zoom out. So using the concept of a contrapositive, so this is more like logic. This used to be covered years ago in geometry, but for lack of better words. So using the concept of contrapositive, and I give you the definition. So switching the hypothesis and conclusion of a conditional statement and negating both. It's a little complicated. So it's kind of like saying if today is Friday, then tomorrow is Saturday. But I could also say if tomorrow is not Saturday, then today is not Friday. So that's the contrapositive. So don't worry about those details too much, but it deals more with logic. So the last line in the preceding box is equivalent to. So if function of a equals to function of b, then that implies that a equals to b. And we're going to be looking at that in more detail. So we're going to use this statement to decide whether a function f is one-to-one in general. So if we look here, so now you should have access to the handouts. This should have been in the learning materials classwork section for chapter 4. So take a moment if you need to access that, if you need to download. I wish I could show you this image that I have in front of me of this blue jay. They're harder to take pictures of, by the way. But anyway, so I hope you accessed example 1. So what we're trying to do, and I'm sorry that the solutions are just there in your face. You know what? I don't think it's a bad idea because it's kind of good for you to see the example and then for us to just talk about the step-by-step. So what we want to do is we want to figure out if this function is one-to-one. So if we have the following, if f of a is equal to f of b, then what we hope for is for a to equal to b. So in this case, we have f of x. So all we're doing is we're plugging in for x a, and then we're plugging in again for x the letter b. So you see f of a equals f of b. The only difference is that the two equations are equal to each other, but x has been substituted for a on the left, and x has been substituted for b on the right. So what happens is when you solve, or we try to, let's say, subtract 12 on one side, or we're trying to basically isolate the variables, we end up eliminating the coefficients, and we end up eliminating the constants. So what we're left with is just a equaling to b. And if this happens, then by definition, the function, although we don't have any points to compare, but if we did, we will see that for every x there is y, or one y value, and for every y value there is one x value. In other words, you would see this. So given what we just did, this would be the end result. So again, going back to this example, in this case, if we have f of a equals to f of b, then a will equal to b, or in other words, the function is 1 to 1. So let's look at this next example. So, decide whether each function is 1 to 1. So here we have the following. So here if we choose a equals 3 and b equals negative 3, clearly 3 does not equal to negative 3. But look at what's going to happen here. So if we plug in, so we're now evaluating, you're going to see why we're doing this. So f of 3, if we plug in and evaluate, it equals to 4. And f of negative 3, if we plug in and evaluate it into this function, it also equals to 4. So here, although a does not equal to b, right, f of 3 will equal to f of negative 3. So although we have a function, it's not considered 1 to 1. So remember, if we go back, so we're going to go back to this example here. Right, so this is where it gets a little bit confusing. So if a doesn't equal to b, then it implies that f of a does not equal to f of b. But by looking at the contrapositive, so basically switching the statements and then giving the opposite values. So if the idea of the contrapositive is kind of confusing, this is what you need to worry about here. That f of a must equal to f of b, or if that is the case, then a will have to equal to b for us to have a 1 to 1 function. So what happened here is this. So we could choose clearly here values that do not equal. A does not equal to b, but it was done purposefully because if you plug in this value of a and this value of b, when you square it, it's the same value. So that when you evaluate this, it becomes 4. So it's kind of looking at it this way. So I'm going to go back to a graphic. Look at it this way here. It's kind of saying this, right? So we had two different values of x, right? So in the example the second example, we had a value of 3 and negative 3. Although they are both different, they resulted in the same output. So if that happens, then we have a function that's not 1 to 1. So in this case, it's a little bit easier to do that. I mean, you could have done this, by algebra or using algebra, and you would have, come across the same value. You would have seen that although they're not equal, right, A or B, that you would have the output being the same. But in this particular case, I wanted to show you using actual values and having it being less abstract. So basically, this is all leading to some type of horizontal line test. So you know the vertical line test. That I think we spoke about when we were still in Academy of American Studies. When we're in the physical building, we spoke about a vertical line test. So now, we looked at it this way. So I'm just going to turn this. So this is what we did before. So we had some type of graph, and if we performed a vertical line test, then what ends up happening is if it goes through 2 points, we don't have a function. But now when we do a horizontal line test, when we do this, then we still have a function, but if it goes through 2 points, then the function is not one-to-one. So again, I'm just going to read what we have here. A way to show that a function is not one-to-one is to produce a pair of different domain elements that lead to the same function value. There's also a useful graphical test, the horizontal line test, that tells whether or not a function is one-to-one. So basically, if this happens here, not one-to-one function. That's what all of this is saying. A function is one-to-one if every horizontal line intersects the graph of the function at most once. So if we look at the second example. So actually, I think you should be able to do this independently. So let me just look at the materials, because I think this, hold on, let me just look. Right, so here, I'm going to let you work on A and B. I'm going to give you 30 seconds here, not even, to determine whether these graphs are one-to-one. It may take you like 10 seconds. And then I'm going to go into the solution. So if you look at 2A and 2B, you have these different graphs. And what we're looking for, we're trying to determine if the graphs that are presented are one-to-one. It probably took you 5 seconds. You probably did this mentally. And if you did that, then that's good. So, another 10 seconds. So 2A, 2B. Do you have one-to-one or do you not have one-to-one? So if we look, 2A, here it's failing. It's failing the horizontal line test. So if that's the case, then you will not have one-to-one function. And let's see what we have over here. What's his problem? Don't mind him. He's just odd. So hopefully that makes sense. Hopefully you find that comical. It all connects though, because we looked at these different types of graphs. So it goes back to the degree of a polynomial. Degree 2, degree 4, degree 3. All right. So here, clearly this should have been one-to-one. And it would have passed the horizontal line test. So in an effort to just cover more content, this I will legitimately let you try on your own, but not during this time. Only because I want to cover as much as I can in the next 10 minutes or so, but I'm pretty sure you could answer A, B, and C within like 10 seconds. Maybe you already did it. But you kind of get an idea of what needs to happen now with functions, with one-to-one, whether the given functions are going to be, one-to-one or not one-to-one. So actually, I'll let you, if you want to take a picture of this, if you want to write it down, this way you can review and try to, figure it out on your own. Please, by all means, take a picture, take a screenshot, whatever you need to do. But I just want to make sure that I cover the next the next section in this handout, or in this chapter, excuse me. All right, so going to inverse functions. So we looked at one-to-one, and inverse functions are related to that. And it's basically what I presented here on the board. So on the digital board, right underneath Fourier, we have xy, and then we have this idea of yx. And I don't think anyone commented on what type of geometric transformation that is. Let's see, wait, hold on. I have comments. First is not a one-to-one. Wait, is that what you're sharing, or is there an error on my end? Hold on. The first one, not one-to-one. Hold on. Okay, yeah. Right, so Josh, Josh, Irene, and Valentina, were you just sharing the solutions, or was there an issue with the solutions that I presented? I'm just curious. I'm sorry. Okay, I believe that you're just sharing your responses. Thank you for that, by the way. Sorry, I just saw the comments now. Alrighty, so going back. So, inverse functions. So, it deals with this. So, it deals with this manipulation, or this changing, or this switching of x, y, and yx. Hold on, I see more comments. I was just answering the first two. Sharing. Thank you so much. Thank you, Irene, Josh, and Valentina. I'm like going between screens. It's kind of crazy. I should take a picture of my workflow. I'll do that at some point. I know, very exciting. Did you guys like the pictures of the scenes from the backyard? You want me to keep doing that? Should that become like a series? Do you want me to just take like random screenshots of like what I find on IG and share them? When there's so much silence, I hear crickets in my mind. Anyway, so, all right, moving along. So we have these inverse functions. So f of x is equal to 8x plus 5, and then we have this function g of x is equal to 1/8 x minus 5/8. So we have that, and in this example, we're just picking a random value, an arbitrary element. So an element is a member of a set. Let's not get too bogged down with the vocabulary. So we're just picking a number at random here. So we pick 10. So if we evaluate 10 for f of x, we'll get 85. So let's see what happens now if we evaluate the other function. So g of x. So now look at what happens. So if we evaluate g of x now with the solution for what we had when we evaluated f of x with 10, I want us to see what happens. So we plug in 85 into g of x. And then when we simplify, we see that g of 85 gives us 10, or basically what we started with. So if that ends up happening, we have what is called an inverse function. So let's look here. So when we started with 10, we put this into a machine. The machine gives us an 85. Now if we put this 85 into a different machine, and it gives us what we started with, then what we have are called inverse functions. So again, what you put in, you get an output. And if you put that output into this other function and get what you started with, then you have what's called an inverse function. So we could pick any number. You know, we just pick 10. You could pick 11, 12, I don't know, 1,000, I don't know, 2020. You plug that in. So these are also other arbitrary numbers. So look at what happens. You plug in f of 3, you get 29, but then g of 29 is 3, and so forth. So what ends up happening is what you start with. You plug that into a different function, or you plug the answer into a different function and you get what you start with, you have what's called inverse functions. All right. So if we look here, in fact, for any value of x, so we did composite notation. We did that already. So basically what you see here, f following g of x, g following f of x. This we did, I want to say, I don't remember if we did it in this environment or back at Academy, but we definitely covered this. So this will allow us to look at inverse functions as well. So basically, this is what's going to happen. I'm just skipping the slide because this kind of sums it up here. So let f be a one-to-one function, then g is the inverse function of f if f of g of x equals x and g of f of x equals x. So basically what we just covered. An input gives you an output, and then that output goes into a different equation or function, and then you get the original value. You have inverse functions. So if we look at this example now this is probably on the second page of the homework. I'm sorry, of the class handout, excuse me. So this should be on the second page or the back of it. So if we look, we have the following. So let functions f and g be defined as f of x equals x cubed minus 1. And then we have here g of x equals to the cubic root of x plus 1. So what we want to know is this. Is g the inverse function of f? So if you were to graph this, it would look as follows. It would look like that blue graph that's in front of you. So that's number one. Number two, does it pass the horizontal line test? And if we look at it, it will. So the horizontal line test applied to this graph indicates that f is 1-to-1. So the function does have an inverse. Since it is 1-to-1, we know then that f of g of x, we have to now find g of f of x, or we have to look for these two. So we have to figure out first if they're 1-to-1. If it passes that, now we have to determine whether they're inverses. So let's look here. So we have this. Functions f and g, we already defined them, x cubed minus 1, and the cubic root of x plus 1. So is g the inverse function of f? So there's only really one way to find out. So if we perform f of g of x, right, or whatever g of x is, we plug that into f of x, and in this case, if we do that, we get x. So if we do now g of f of x, and we end up with this value here, x, then they're clearly inverses. So that's what we're going to test here in this next slide. And if we do that, and again, just look at the examples, we'll see that we end up with the same value. So since this is happening, we have inverse functions. So something to pay attention to here, that we're going to use special notation. So this special notation, it looks like f to the negative 1 power, but it's really read as f inverse. So when we had f of x equals to x cubed minus 1, g of x should have really been written as f, it looks like the negative 1 power of x, but it's really f inverse of x. And that would have been equal to the cubic root of x plus 1. So, I think we've run out of time. So what's going to happen, I have some homework posted. I'm going to clarify which questions you need to answer because we only went through so much of this, and I don't want to, give you too much homework for the weekend. So other announcements. So next week, we're only going to meet for 2 days. We're off on Friday. I hope you're aware of that. and you probably have a question as to what's going to happen during spring break. That's still to be determined. Your spring break, I'm sorry, it has been canceled, but they're trying to figure out exactly what's going to happen that week. More details will be provided. I still don't know yet what's going to happen because it's college now, but I'll keep you posted. The only thing that I can confirm is this, that we have class definitely Monday, Tuesday. We're off next Friday, and then we have to figure out what's going to happen on spring break. So I will adapt the homework that's going to be due on Monday, and I'll share some other information in our classroom main page. Do you have any other questions for me? All right, so I'm going to take that silence as no. Great class today. I hope you have a great day. I hope you have a great weekend. I'll see you on Monday. Stay safe, stay healthy, and that's it for today. Have a good one, everyone. See you later.